guys, we just wrapped up test 2, so new unit for us. If not obvious, this unit is going to be on integration. Now before I jump in head first to this unit, I did want to make a couple comments. The whole point of Calculus 3 is to investigate what happens if you take calculus and allow ourselves to work in more than just single variable functions, right? So what happens when we pop things up to higher dimensions? Something that I want to note before we start seeing it a lot is that when we add those higher dimensions, we're going to be able to develop a whole bunch of different kinds of integrals, and also we're going to see a whole bunch of challenges that'll pop up just based on the geometry of being in higher dimensions than what we were working with before, okay? Those higher dimensions are going to complicate things. So a big focus is what kinds of tricks can we use to take the integrals that we need to work on and rewrite them into simpler integrals that we know how to compute with, or that we know how to work with, right? So case in point, I'm going to go ahead and kick off this section by jumping back to section 10.3 on polar coordinates. Now you may be wondering why we jumped back to 10.3. We were doing double integrals in chapter 15. We'll get there, okay? We are still going to be focusing on double integrals, but a big problem for us here that I wanted to tackle by coming back to this section is that sometimes these double integrals can be a pain to integrate if the region that you are trying to integrate over is circular, right? If this guy is a circular region. Now, it's maybe not super obvious why it's a pain, or how this pain ends up manifesting, but I'll try and demonstrate, right? So I've got this example below. Try to compute this double integral of x squared plus y squared, where the region that we're integrating over is the unit disk. Okay, now on the surface, it doesn't look like too bad of a problem. We've got a polynomial function. A circle is a pretty simple looking region. But anyway, let's give this guy a go. I'll scroll down and give myself a little bit of room to try and tackle this here. Okay? Now, if I do the naive approach to this and just try to set this up like any other problem that I've given you in the double integral section, let's see how this goes, right? First thing that I want to do is get my bearings. We all know what the unit disk looks like. Okay, I've got this circle, okay, radius 1 here. And just to, clarify, circle radius 1, the equation for that is x squared plus y squared equals 1. Now, how this fits in with us setting up the double integral is I need to know what my bounds are, and this guy right here is a general region, right? That means that I should hopefully try to set this up as either a type 1 or type 2 integral. In this particular case, it doesn't really matter, but I feel like most of you guys usually like type 1 a little bit better. So we'll go that route, right? If I want this as a type 1 region, I need to find my function bounds on y. I can find those by taking the circle equation and solving for y. You are going to get two solutions back, plus or minus square root of quantity of 1 minus x squared. And the reason that you get two solutions back is that one of these corresponds to the upper portion of the circle, and the other one, well, that corresponds to the lower portion of the circle. Okay, so how this is going to manifest itself in our bounds is that, this negative version of the square root, that's going to be my lower bound on y. And the positive version, that's going to be my upper bound on y. Now, we've got my function bound sorted out. That means that there should be some sort of numerical bounds on x. Well, it's a circle of radius 1, so just looking at the picture, shouldn't be too hard to figure out. If it's radius 1, we can only go backward 1 unit and forward 1 unit. So x has to be stuck between minus 1 and 1. Now, since I have those, I can actually insert these into my integral, right? We know that the numerical bounds have to go on the outside, and the function bounds have to go on the inside. Once I copy my integrand over, the only thing that I have to do now is make sure that my order of integration matches up with these bounds. So those functions, they were bounding y. Those numbers, they were bounding x. This is the order in which I have to set up my integral. Now, if I want to scroll down and give myself a little bit of room to compute this or take a first pass at it, we're working with integral with respect to y first. So that means we can leave all this stuff on the outside alone. We're not going to touch it just yet. I have to take an antiderivative with respect to y. Okay, so treat y like my variable and x like a constant. And then I have to evaluate this integral at my bounds, right? Y was supposed to be stuck between positive and negative square root of 1 minus x squared. Now, when you go to evaluate those, we do know that you have to substitute in your top bounds first. So I'll get a x squared times this root, plus I'm going to kind of condense my powers here a little bit. This will look like 1 minus x squared to the 3 halves over 3. Reason being for that, if you take this thing and plug it into the cube, you know, the 3 in the numerator, that's your original power. The half power here, that's coming from the fact that you had a square root. So this is basically what happens when you plug that top bound into y. And I still have to subtract off what happens when I plug in my bottom bound. Well, actually, let me write my minus sign down here to give myself a little bit more room. If you go to plug that thing in, you're going to get something that looks very similar to what we just got. Okay, comments about the powers included. Okay, reason that we get this is because most of those powers we were dealing with are odd. Odd powers don't suppress negatives. So, since these guys look so close to each other, we may as well combine like terms. Okay, so this will actually get rid of half of the clutter that we're seeing here. You may notice these guys, if I'm subtracting a negative, really I'm adding pretty much everything here. And these first two terms look alike. That means that I've got two copies of them, so I really have 2 x squared times root 1 minus x squared. And then same deal with the fractions on the end. I've got 2 of those guys, so I've now got a coefficient of 2/3 on this thing. Now, before I go and spend any more time working on this integral, hopefully y'all are on board with me by now, the fact that this looks like a giant pain in the butt, right? We started out, I'll scroll back up here, with this super simple looking function over this super simple looking region, and we've got this hot mess right here. Now, some points to highlight about this integral. How might I tackle this? Well, you actually can do this using your Calculus 1 methods, just it's not going to be the most pretty. So I'll go ahead and note that if you do want to look at this from here, you need to dust off your trig substitution. You know, you can't do this as a parts or as a u sub integral. The compositions don't quite work out right. My inside functions are all squares. I have no linear terms multiplied by them. Okay, so trig substitution as a first pass. All right, maybe if you remember trig substitution, not too bad. You're going to get a whole bunch of trig terms in that. That means that you're going to have to treat this guy as a trig integral. And what I mean by trig integral, you know, I think this was like section 7.3 for your trig sub. Maybe section 7.2 for your trig integrals. This was that section back in Calculus 1 where you're using all sorts of obscure trig identities and pairing it with u substitution to try to get things to work nicely. If you don't believe that I'm saying that this is a nasty problem, well, here's some of the work, right? Looks fun, right? So I'm not super focused that y'all actually know or remember how to do all of this. Just the point was that integral was long. Very, very long. So much work just to get to this point down at the end here. And screw doing that, right? I told you guys that integrating over these circular regions is sometimes a pain. We've seen it's a lot of pain. So what can we do to not have to work problems that look like that? Well, a suggestion that we have, and the reason that we're in this polar coordinate section, is let's see if we can screw with the coordinate system and get it to make things nicer. Now, what I mean by that is this. Y'all are pretty used to the standard Cartesian coordinate system, which looks like this. I give you a point in this system. That point corresponds to an ordered pair where I give you an x value and a y value for that pair. Okay, so I'm assuming I've got an x and a y axis here just so I'm not skipping out on my labeling here. Now, what I mean by screwing with the coordinate system is this. Just because I give you guys an ordered pair of numbers to refer to the location of points in space, it doesn't mean that we have to use this Cartesian system. I could give you two numbers and we can try to reference things in a slightly different way. Namely this. So the polar system, my polar coordinate system. The idea for this, even if we're on the same set of axes, is this. The two numbers that I give you now, these are going to be an r and a theta, not an x and a y. So these are going to be two totally different numbers. Now, where are these guys coming from? Well, for your r, here's a new idea. What I'm going to go ahead and do is draw a segment that connects that point that we're trying to reference to the origin, and I am going to measure the length of that segment. So that distance from the point to the origin, that's going to be r. Now where theta comes in, you see this angle that happens between the positive x-axis and my segment. Well, that angle is going to be my theta. Okay, so in short here, if I'm going to scroll down, in your polar coordinates, okay, whenever I give you r theta as an ordered pair, we're no longer talking about how far on the x-axis or y-axis we are. We've got a distance to the origin, and we've got an angle between the positive x-axis and the segment that contains the origin and our point. Okay, so let's just try an example real quick, right? Plot the polar point, 5 pi over 2. Now again, this is me trying to reference an r theta point, not an xy point. So if I draw my axes out, okay, standard x, y axes, I want to consider this. If I'm giving you guys that my theta is pi over 2, this means that I'm starting with the positive x-axis and I want to go over basically to an angle that is pi over 2 from that positive x-axis. We measure that in the standard direction. So here's my pi over 2. If you go over that far, it basically puts you somewhere on the positive y-axis. And then if you want to know how far up, that's what the r is for. So this is going to tell me I go up 1, 2, 3, 4, 5 units on this y-axis, so that that point right there is 5 pi over 2. Okay, so really what's going to happen is, you know, I want to gauge, I don't know if I'm spelling that right or not, but gauge how far, you know, your angle has us go over. And then, how far out. This is going to be what my r is for. Okay. Now, some comments on this. Got two notes for you. First off, in that past example, I did give you two positive values. You know, how far over am I going, you know, angle-wise. I don't necessarily have to give you a positive number for this theta. Typically, if we're, you know, kind of trying to stay within a standard range of angles, mostly best practice is for us to stay within 0 to pi. You don't have to do that. If I had given you guys pi over 2 in that previous example, if I had given you pi over 2 plus 2 pi, okay, notice that doesn't actually change my angle. We can do that, okay? So my angle can fall outside of that range, but if you're worried about giving somebody polar coordinates for something, usually we want to try to stay inside of the range 0 to pi as best as we can. Second note that I wanted to make for you guys is this. Again, I also highlighted, negative values of r. These guys are potentially a thing. How do I interpret that? How do I interpret negative distance from the origin? Well, the trick for that is this. Head in the opposite direction of your given angle, right? So if you're given a negative r, what you want to do is head backwards, right? So best practice, if you are converting, if you have a choice to try to name a point, try to pick a positive r. It's the best practice to do that. You don't necessarily have to, though, okay? So kind of what I'm trying to get across in both of these notes is that polar coordinates, one downside for the system is that my coordinate representation actually isn't unique. We can have multiple points, represent the same exact spot in space, right? So if I want to give you concrete examples, maybe relevant to this thing that we just did, I had just given you 5 pi over 2, okay, in that above example. I just said if you take pi over 2 and you add 2 pi to it, so the same thing as 4 pi over 2. If I add that on, these guys are the same exact point in polar, okay? So if you just keep looping around and around and around but landing on the same angle, you get the same point. For these negative values, this one maybe makes sense a little bit better if I draw you guys the picture. Here we said that here is this, angle of pi over 2, and we head out 5 units in that direction, okay? I could alternatively try this from a different approach. Let's say maybe I use a different angle, so this would give me something like minus pi over 2. And if that's the angle, okay, that I'm working with, well, you notice that this point that we did in the last example, this is 180 degrees in the opposite direction, okay? So if I wanted to use this negative pi over 2 and travel in the opposite direction from that angle, well, I just have to give myself a negative r to compensate, okay? So do keep in mind, you don't necessarily have unique representation of points. With that said, how the heck do I convert to these things in the first place? Well, here's some tricks for our Cartesian polar conversion, right? Let's assume that I've got some sort of an xy point that I want to start with, and I want to turn this into an r theta coordinate, okay? Now, the idea here, use geometry and trig. It's actually not too tricky if we think about the fact that you can construct a right triangle in the middle of this picture, right? Here's my angle. The r that we want is very clearly going to be the hypotenuse, and down here I've got a length in the x direction and a length in the y direction, right? So hopefully this one's pretty clear. If you're looking for the r in your r theta conversion, use the Pythagorean theorem, right? We expect x squared plus y squared to come out to r squared. If you solve for r in that, this is what you get. Now technically, if you solve for r in that, we get the two different values. One's positive, one's negative. We've already mentioned this a moment ago. Best practice, if you have the choice to convert, use the positive version of r. Okay, so that's why we're trying to kind of gloss over that right now. It'll make our work a little bit easier. If you have the choice, try to pick the positive version. Now, as far as the theta goes here, I said use geometry or trig. Something that I want to point out about this triangle, with this angle theta, if I view this as a reference triangle, I'm given x and y. That means that I have an opposite side and an adjacent side for this angle, so I can SOHCAHTOA this one out, right? So my tangent theta, this is basically going to be my opposite side over my adjacent side. I'm just going to get tangent theta is y over x. Okay, so again, where we're pulling these from, this guy is my Pythagorean theorem, and this guy is my SOHCAHTOA trick. So basically my trig trick for how to get back my tangent from a reference triangle. And a comment that I will go ahead and make, you notice that I wrote tangent theta is y over x instead of theta is tangent inverse of y over x. We'll touch on that in a moment, but my warning right now is to be very, very careful with your quadrants. This is why I'm expressing this in this manner. If you just use the tangent inverse version, you have a small chance that you might screw yourself over. Okay, so we'll talk about that in a moment. Now, on the other hand, let's say that you've got polar coordinates, you want to convert these back to Cartesian. This is going to be more SOHCAHTOA, and it's actually something that hopefully looks pretty familiar. X should be r cosine theta, and we should have that y is r sine theta. Okay, so one more thing that is going to give me my SOHCAHTOA, if you think about y over r or x over r, this is basically your x over r is adjacent over hypotenuse, y over r is opposite over hypotenuse. Hopefully this is pretty clear. Okay, so just solve for x or y in those. The reason that I'm saying that this is something that's hopefully familiar, this is a lot like in my projectile motion section that we covered a ways back. Whenever we had to decompose the horizontal and vertical components of velocity, we basically used this exact same trig trick, okay, to do that decomposition, okay? So this shouldn't be super new. We're just using, prereq geometry, okay, to make these conversions. Now, if you want to try some examples with these, let's say that we start with this one. Polar coordinates to Cartesian. Again, this should be pretty straightforward given our formulas here. I'm assuming, since I named these as polar, here's an r and here's a theta. Okay, you should always be told, or it should be clear from the context, which coordinates you're being given or which ones you're working with. I'm straight up telling you this is r and this is theta. I just need to stuff these into my formula to get my Cartesian coordinates back, right? So if I'm worried about my x, this should be my r times my cosine of 2 pi over 3, and that means that my y should be my r, which is 5, times my sine of 2 pi over 3. If you go to simplify these, well, 5 times negative a half, or negative 5 halves here. Y should be 5 times root 3 over 2. So, putting these things together, you should get this point, minus 5 halves, comma, 5 root 3 over 2. Okay? Plug and chug. If you're going from polar to Cartesian, pretty straightforward. Not a lot of room for error there. Now, on the other hand, if I'm going backwards, converting Cartesian coordinates to polar, okay, that means I outright told you this is Cartesian, so this is, sorry about my pen blurbing out here. This is x comma y. We have said that your r should come from the Pythagorean theorem, right? R is my square root of x squared plus y squared. I can go ahead and fill that in. We are trying to shoot for the best practice version here, so I'm not worried about the negative possibility for r. I'm just going to work with the positive version. I'll get a square root of 18. Now my theta, on the other hand, right, we said that my tangent of theta was supposed to be my opposite over adjacent side. Well, that's going to be minus 3 over minus 3, right? So this should have been my y over my x. So ultimately, I'm getting that tangent theta is 1. Now, here is the reason why I didn't give you guys the formula in terms of tangent inverse, right? I'm going to point out that tangent inverse, this guy pretty much only returns values that are going to be in the range from minus pi over 2 to pi over 2. No other angles. If you stick stuff in your calculator, this is pretty much all you're getting back is the stuff between minus 90 degrees and positive 90 degrees. That totally leaves out 2 quadrants, and depending on the point that you're looking at, maybe that's a problem. You know, this thing should be sitting in quadrant 3, but that doesn't have anything to do with any of the angles that the inverse function is going to spit out. So the point that I want to make here is think about your quadrants, right? If you expect that your tangent inverse of 1 is the angle that gives you that is 45 degrees or pi over 4, keep your quadrant in mind, right? My point is in this quadrant 3. What's the angle that gives you the same exact tangent value, but it's in quadrant 3, okay? Well, you basically have to add pi to that to get the appropriate angle. This really means that we want to use 5 pi over 4 instead, okay? So I pair these things together, my r and my theta, I am expecting root 18 comma 5 pi over 4. Please, please, please watch out for those quadrants, okay? Now, here's the reason that I'm wanting to talk about these coordinates. You know, we've got the conversion back and forth, we've got plotting points discussed. I said the reason that we wanted to talk about this was to help us figure out integrals. Here's why. If I'm talking about graphing polar regions are pretty much set up to talk about round things, right? If I give you a collection of polar intervals, chances are you're going to be able to represent round regions pretty easily. Now, if you compare that to Cartesian, you know, a pair of, you know, intervals in x and intervals in y, this is going to give you a box, but this is not going to hold the same for polar, right? If I give you a interval of r values and an interval of theta values, we get something very, very different, right? So, for example, let's say I check this guy out here. I've got theta ranging from minus pi over 6 to pi and a positive r. Here's what this region is going to look like. Okay, we've got a theta which could possibly be minus pi over 6. Okay, that's roughly going to be about here. Okay, if this is my xy plane. And my theta can also go to pi, so that'll actually be my negative x-axis over here. Now, if I'm trying to, you know, pick out using positive r, so we actually go in the direction of the angle that we're specifying and not backwards, this means that pretty much any of the angles in this range are fair game. And what r does is it tells me how far outward from the origin I can go. And since I've pretty much said, hey, as long as r is non-negative, we're good, I can head outward from the origin as far as I want, as long as I'm within range of these angles. So if you're wondering what region this looks like, it's pretty much everything that falls, in this span between these angles here. Okay, so you've kind of got this awkward pie slice that I've taken of the XY plane. Now, some comments here. I'll go ahead and note varying your theta with your positive r. This is going to basically give you one of these pie slices. This is a pretty hefty pie slice, by the way. Another comment I'm going to go ahead and make. Told you guys best practice for these points is to try and not use negative values for theta or for r. If you're trying to keep a continuous interval like this is probably one of the rare exceptions, right? So intervals, trying to keep these continuous and in one piece, these are one of the few cases that will okay these negative values for theta. Okay, reason that I specify that is instead of saying, oh, theta has to be between 0 and pi, or it has to be between 11 pi over 6 and 12, we don't want to do that. We don't want to break it up into two pieces. This is one of the few exceptions to that case will allow negative theta. Now, as far as other regions, I said that, for polar regions, this will help us plot things that are round. This will maybe demonstrate this a little bit better, this other example. Let's say that I restrict my r's, but I let my theta vary across everything instead. Okay, so slightly different case. Well, if my theta is allowed to run the gamut from 0 to 2 pi, this means I basically can go all the way around here. But you notice that I'm restricting where my r can go. Now, if I'm saying r is stuck between 2 and 3, and r is my distance from the origin, this says that everything that I can do has to be, possibly 2 units away from the origin, greater than that, or it has to be less than 3 units away from the origin. So what I've actually done here is I've created an annulus, right? Everything inside of this ring as my region, you notice my distance from the origin is somewhere between 2 and 3, assuming that these guys are circles, and my theta I've allowed to vary, right? If I had let r shrink down to 0 here instead of 2, we probably would have gotten the full disk. So I'll go ahead and note, restricting my intervals of r, okay, my intervals of r, these guys can give us rings, or if you go down to 0, maybe disks. And another thing that we can do is actually combine kind of these techniques to get different pie slice looking regions, right? So if I pair both of those together, let's say that I try to sketch this pairing of intervals for you guys. I'm going to go ahead and look at the values of theta that I specified here. I said that we're between 0 and pi over 2, but that my r is only allowed to vary between 0 and 1. So if I go 0 units away from the origin, I'm at the origin. If I only allow myself to go 1 unit away from the origin and have that as my boundary, this basically gives me this region here. If I wanted the full circle, we could just let the angle go all the way up to 2 pi. So hopefully we can see that varying these intervals, instead of integrating over some messy function, maybe if I have something around, and we'll investigate this in the next section, I might be able to use these numerical bounds to help me out a little bit.